Central limit theorem. In our last few lectures, we mentioned about central limit theorem. Here, let us see what exactly is central limit theorem and what is its significance. We are going to go deep into this so that you understand exactly what this theorem says. First, we'll take the statement of this theorem and then we'll analyze each part of it to understand what exactly it states. Okay, this is what central limit theorem says. Central limit theorem, it says if you take a large number of independent and identically distributed random variables, then the normalized mean of those random variables will always tend to follow a Gaussian distribution, and this happens irrespective of the original distribution of random variable. Whatever be the original distribution, if you take independent and identically distributed random variables, then their normalized mean will always tend to follow Gaussian distribution. Let us now see each part of the statement and understand what it exactly means. First part is, if you take a large number of independent and identically distributed random variables. What does this mean? This means, let us say you have some random variables x1, x2, x3 and so on. If this is the case, when will they be independent? If they want to be independent, that means knowing the value of one random variable will give you no clue about the value of other random variables. For example, if we just take two random variables x and y for simplicity, probability of x and y happening will be equal to probability of x happening independently into probability of y happening independently. Why is this so? This is so because whatever be the probability of x, that will not influence the probability of y at all. For example, if you take x as an event which says some particular political party P1 is winning this election. There is some particular election and let us say x says probability of that one party P1 is going to win. And if y says that some party P2 is going to win, then what is the probability of x? Let us say you know the probability of x. If you know that, then this gives you some clue about the y occurring. That is, you already know the probability of y. Why is it? Because let us say if you know probability of x occurring is 100%, that is, you are 100% sure that party 1 is going to win. That means you already know that probability of y occurring, that is party 2 winning, is 0%. This means these two are not independent. If they are independent, then you will have no clue about the probability P2 if you are given the probability of P1 happening. So if you know probability of x, for example, let us say x is the same thing, that is probability of a party P1 winning the election, and y, let us say y is the probability that it is a rainy day. So these two things do not have any link in between. Whichever be the party winning the election, that will not affect the day being a rainy day at all. So if you are told there is a 100% chance that party P1 will be winning the election, you have no clue about whether it will be a rainy day or not. So this is when they are independent random variables. Okay, so this is the concept of independence. Second part is identically distributed. What is identically distributed? Identically distributed means all your random variables, they all follow the same probability distribution. That is, if one variable is coming from a uniform distribution, all others will also come from uniform distribution. If one is coming from a Gaussian distribution, all others will also be taken from a Gaussian distribution. If one is coming from a, let us say, Laplace distribution, the rest will also be from Laplace. This is when you call it as identically distributed. Okay, so as of now you understood what is independent, what is identically distributed. Let's get back to the statement of central limit theorem. You have taken a set of random variables, a lot of random variables, large number of random variables. All these are independent of each other and they are identically distributed. Then What is the statement? The normalized mean of those random variables will always follow a Gaussian distribution. Let us first understand what is normalized mean or standardized mean. What is this concept? This means, I'll erase these things off. Let us understand standardized mean. First, we'll go to the concept of mean of these random variables. Then we'll see what is the sample mean and what is the normalized mean. Okay. We are taking these random variables x1, x2, x3, etc. If these are the random variables, then let us say the mean of these random variables is mu. And the variance of these random variables is sigma square. So for these random variables, I'm telling you the mean is mu and variance is sigma square. Mean means the expected value of the random variable. Okay. This is mu and variance is sigma square. If this is the case, then what will be the sample mean? What is the difference between mean and sample mean? Here I told this is the mean and I am going to calculate sample mean. First I'll write the formula, then it will be easier for me to explain what is sample mean. Sample mean xn bar, I'll call it xn bar. This is equal to 1 by n sigma I is equal to 1 to n xi. This is what I call as sample mean. Now you would have got some idea about what is sample mean and what is mean or expected value. The difference is expected value, whatever is the expected value, that is the true average of the underlying random variable x. Let us say all these are coming from some distribution and the underlying random variable x will be having a true mean. That is what you call as mu, the expected value. But what is the sample mean? Among the samples you got, x1, x2, x3, these are the samples that you got. If you simply take all these samples and you average it out, what you get is the sample mean. I'll take an example, a numerical example so that the concept is clear to you. Let us just take a case of rolling a die. Okay, the die can take values 1, 2, 3, 4, 5 and 6. These are the only values. So what is the expected mean, the true average, the true mean of the random variable x? Let us say underlying random variable x, which is showing the single throw of a die and it can take values 1, 2, 3, 4, 5 and 6. Then what is the expected value? The true average of x, that will be 1 plus 2 plus 3 plus 4 plus 5 plus 6 whole divided by total number of these occurrences 6. So this will give you 3.5. So 3.5 is the expected value or mean. Mu is 3.5. This is the expected value. What about your sample mean? Let us say these are the values x can take. But let us say you did some experiment. In your experiment, x took values 1, 1 and let us say 4. These are the values that x took when you threw the dice 3 times. So this is the sample that you have. Your sample as x1 is equal to 1, x2 is equal to 1, x3 is equal to 4. These are coming from underlying random variable x, which is having an expected value 3.5. But when you threw the dice, in your samples, the values that you got are 1, 1 and 4. So your sample mean will be 1 plus 4 divided by total number of samples 3. So this will be 6 by 3, that will be 2. So if you see this, your actual mean or true average or expected value is 3.5, but the sample mean is 2. This is the difference between sample mean and expected value. Okay, so let's proceed back with central limit theorem. I just wanted to clarify so that you don't get confused. Let's proceed with central limit theorem statement. What does it say? We are going to find normalized mean. This is what we want to find. As of now, you understood what is mean, expected value, what is sample mean. Next step is you want to find normalized mean. So normalized mean is sample mean xn bar. This you have to normalize. How do you normalize sample mean? If you want to normalize or standardize, what will you do? In order to standardize, you have to subtract this from mean. Subtract mean from this and then divide it by standard deviation, which is sigma by root n. So I know you'll be confused here on why I took sigma by root n as standard deviation instead of sigma. We'll clarify that. First of all, when this is what central limit theorem says, when n tends to infinity, that is when you have a lot of very large number of random variables, then the normalized mean, that is given these are independent and identically distributed, then the normalized mean of this is the value, that is sample mean minus the expected value divided by standard deviation. The normalized mean, this will always be always you can, this follows a Gaussian distribution or normal distribution, you can say n0 1, that is it has a mean of 0 and variance of standard deviation of 1. So this is the statement says when n tends to infinity, when there are a large number of identical and independent and identically distributed random variables, then the normalized mean will always follow a Gaussian distribution irrespective of the original distribution of variables. So now let us clarify why this term is sigma by root n. Why did I standardize like this? The reason is, first part, this part is clear, right? This is sample mean, this is the expected value. So you are standardizing the mean. For that you want to subtract expected value and then you want to divide by standard deviation. Why are you doing this? Because your sample mean may have any mean. So the value can be anywhere, which means your graph can be drawn at any point. Instead, if you take the difference from the actual mean, that will give you a standardized value irrespective of the distribution you are taking or irrespective of the samples you are taking. So when I say that you will always have a normal distribution, that is a one with 0 mean and 1 variance, when I say this, I should standardize any given sample to one particular scale. So taking all those into one particular scale is this process of standardization. Okay. So in order to take it to same scale, what will you do? You will have an actual value which is sample mean. You will subtract the expected value from it so that the center is aligned. Next thing is deviation can be different for different ones. So now you want to align deviation. For that you will divide by standard deviation sigma by root n. Next we'll clarify why is this sigma by root n? You know standard deviation is sigma. Why did I take sigma by root n here? I already told you that the variance of distribution is sigma square. Then why did I take sigma by root n? The reason is, I'll show you. See, if you see this, you already know the variance of your underlying distribution is sigma square, right? Which means standard deviation will be sigma. This is already known because if variance is sigma square, standard deviation will be sigma. Then what you actually want to take here is the variance of your sample mean, because you are considering your sample mean, and when you're doing calculation you want to take not variation, it is standard deviation of your sample mean. What you got here is the standard deviation of your underlying distribution. This is the difference. Standard deviation of underlying distribution of the random variable x. That random variable x has a standard deviation of sigma. This is the true standard deviation. What you want is the standard deviation of your sample mean. So how do you take that? So first we'll take variance, we'll calculate variance and we'll take square root. That is the easier way because variance is sigma square, standard deviation is sigma. So when you want to calculate standard deviation, what you do is you'll calculate variance and then you'll take square root of it. Then you'll get standard deviation. Okay. Let us find the variance of sample mean xn bar. How can you calculate the variance? This can be calculated as, this is your sample mean. That means variance of your sample mean, I'll take a bit more space here. That means variance of your sample mean, this can be written as variance of 1 by n sigma I is equal to 1 to n, I is equal to 1 to n xi. So I just substituted the formula for this xn bar sample mean. Then I got this variance of 1 by n into sigma I equal to 1 to n xi. This can also be written as, I am simply taking this 1 by n outside. What happens if I take 1 by n outside? it will be squared. This is basic variance operation formula. If you take this constant outside, it will be squared. So this will become 1 by n square into variance of sigma I is equal to 1 to n xi. This is what happens. Once you got this, next thing is you want to again simplify this. Is there a way to take this summation term outside of variance? Yes, there is a way. What can you do? So variance can be written as, instead of this, now you can write it as 1 by n square. You take the summation outside, sigma I equal to 1 to n. Then you do variance of xi. See, both are one and the same. Mathematically, both are one and the same. I just took the summation part outside. When I do this, the inner term becomes variance of xi. But you already know what is variance of xi. What is variance of xi? It is sigma square. It is known to you. Given that you know that, you can substitute variance of xi sigma square here. I equal to 1 to n sigma square, which simply means n times you are summing sigma square. N times sigma square is n into sigma square. So this will become 1 by n square into n into sigma square. That is equal to sigma square divided by n. So this is the variance. If variance is sigma square by n, then what is your standard deviation? If the variance is variance of your sample mean, if that is sigma square by n, then what will be the standard deviation of your sample mean? That will be square root of variance, square root of sigma square by n, that is equal to sigma by root n. So this is my standard deviation. That is how I got this particular value here as standard deviation. Okay. So this is the standardized mean. So at this point you understood what is independent and identically distributed. You understood what is normalized mean or standardized mean. This is the value. And then now when you look back at the statement again, everything will be clear. What is the statement? If you take a large number of n tends to infinity, large number of independent and identically distributed random variables, then the standardized mean of those random variables will always follow a Gaussian distribution irrespective of the original distribution of variables. This is the statement. So in another way you can say that standardized sample mean always converges to a standard normal distribution. This can be another way of stating the same thing. Standardized sample mean always converges to standard normal distribution. So simply, even if the original errors aren't Gaussian, that is, we were discussing about errors in the last lecture, so I'm relating to that. So even if your original errors, even if these are not Gaussian, still when many small independent effects add up, that is, it can be sensor noise or maybe biological variations or maybe economic fluctuations, any sort of data that you're having, when all the independent errors add up, what happens? The result always tends to be approximately Gaussian. So this is the reason why we said in the last lectures that MSE is widely accepted. Why is it widely accepted as a loss function? The reason is mean squared error. We already discussed how this is related to Gaussian. So given that these errors, irrespective of the original distribution, errors always tend to follow a Gaussian distribution. Because of that, MSE becomes relevant, because even if you don't know the underlying distribution, you can confidently apply loss function MSE, mean squared error, because you know that when a lot of errors add up, they will automatically follow Gaussian distribution. So MSE becomes relevant there. This is the statistical significance of MSE. So in another way, you can say CLT, the central limit theorem. Central limit theorem justifies using normal distribution to construct confidence intervals. That is, irrespective of original distribution, even if you don't know the original distribution, usage of normal distribution is justified by CLT, the central limit theorem, right? One more thing I'll do is, in order to make all these put together and make you understand in a simple manner, I'll show you an example on how it is converging it into a normal distribution, right? I simply told you that when you have a large number of inputs, large number of random variables, and if you take sample mean, it will always follow Gaussian distribution. I will take a numeric example and show you how it is converging to a Gaussian distribution when you increase the number of samples. Okay, this should make everything very clear for you, right? What I'll do is, we'll take a simple example of rolling a dice. Okay, you are rolling a dice. What happens now? Original distribution is a uniform distribution for rolling a dice. Surely it is not Gaussian. So I want to tell you that it is actually not from a Gaussian distribution, but you will see that when all these add up, the sample mean always tends to Gaussian distribution. That is what I am going to prove. So initially, rolling a dice is surely not coming from a Gaussian distribution. The original distribution is uniform. What are we going to do? First of all, you will simply roll the die once. Okay, if you roll it once and repeat this experiment a lot of times, let us say you repeated this 1 lakh times. What happens? If you repeated 1 lakh times, each time you rolled it once. If that happens, your distribution will be uniform. If 1, 2, 3, 4, 5, 6, these are the values. 1, 2, 3, 4, 5, 6. Your distribution will look somewhat like this. It will be uniform. The value, number of ones will be same, twos will be same, threes will be same. All these counts will be same. See, it will not be exactly same, but I'm saying if you roll it 1 lakh times, then somewhat the number of ones in it, number of twos in it, number of threes in it will all be almost the same. So it will be a uniform distribution. This is what will happen when you roll it 1 lakh times. Each time you record the value that you got, because it is random occurrence. So 1, 2, 3, 4, 5, 6, any of these can occur with equal probability. So your distribution will look uniform. Next experiment is, instead of doing it once and doing it 1 lakh times, this time, okay, I'll put it other ways. 1 lakh times you rolled it once. This time what you're going to do is, you'll again repeat it 1 lakh times, but this time in each of these experiments, what you're going to do is, you'll roll it 10 times and take the average. Instead of simply rolling it once, you'll roll it 10 times and then take the average. This time what happens? The average of 10 rolls, this coming to 1, the chances of average being 1 is very less. Because if average has to be 1, in all the 10 rolls, the value should be 1. Then only you will get average of 1. So the chances are that your average will be somewhere near to 3.5, the actual average, but there will be fluctuations. So if you do 10 rolls, what will happen is, this time, I'll draw here only. This time your histogram won't look like this. Instead, number of ones will be very less, number of twos will be slightly larger, threes will be slightly larger, fours will be here, something like this it will show. So this is what happens if in each of the 1 lakh experiments, you will roll it 10 times and take average. Average is what you are recording. In third experiment, you will again do it 1 lakh times, but the difference is, this time you will, in each of these experiments, you will roll it 100 times and take average. If you do 100 times and take average, this time it will look more Gaussian. This is what is going to happen. It will be more of a bell curve. It will look more Gaussian. If you keep increasing this 100 to a larger and larger number, and you increase this total experiments as well, you will see that you will get an exact Gaussian distribution. So this is what central limit theorem says. It will converge to a Gaussian distribution as you do take a lot of random variables. If you take large number of independent random variables, then the sample mean will always follow Gaussian distribution. So this is the central limit theorem.